All right, let's dive in. Today, we're going to trace the entire story of modern AI all the way back to its origin, to a single brilliant and surprisingly simple idea, the first artificial brain cell. Before we got to all the incredible things AI can do today, the pioneers had to solve a much more basic problem. Forget poetry, forget driving a car. How do you even get a machine to make a simple choice, a yes or a no, an on or an off? That was the real starting line. So if you're trying to build an artificial brain, where do you look for inspiration? Well, you look at the real thing. On the left, you see a biological neuron. And man, it is complicated. The real genius of the early researchers was that they didn't try to copy it exactly. Instead, they simplified it. They created a clean, mathematical model, the artificial neuron on the right, that just captured the essence. It takes in some information, decides how important each piece is, and then makes one simple decision: to fire or not to fire. So let's start right there, with that very first attempt to build a thought process, not out of flesh and blood, but out of pure math. And, this all happened way faster than you might imagine. The first big idea, the McCulloch-Pitts neuron, came out in 1943. But then, just over a decade later, in 57, we get the perceptron, which could actually learn. And then boom, only 3 years after that, Adeline comes along and makes that learning process even smarter. It was a whirlwind of innovation. So this is it, the MCP neuron, the granddaddy of them all. And its core idea was beautifully simple. Just think of it like a bouncer at a club. It checks a bunch of IDs, the binary inputs, and if enough of them are valid to meet its rule or its threshold, then it lets a signal through. It fires. It was just a static model, but it was a brilliant first step in modeling a decision. Okay, but a model that just follows a fixed rule isn't really intelligent, right? The real magic, the next giant leap, was figuring out how to get this thing to learn from its experience, to actually get better on its own. And that brings us to Frank Rosenblatt's perceptron. This, right here, was the absolute game changer. It wasn't just a static calculator anymore. It was an algorithm with a built-in rule for self-improvement. For the first time, we had a machine that could actually learn from its errors. So how did it learn? It's this elegant three-step loop. First, it makes a guess based on the information it gets and the weights it assigns to them, basically how important it thinks each input is. Second, it checks its guess against the right answer. And third, this is the magic part. If it got it wrong, it adjusts those weights, so it's a little bit less wrong the next time around. That's it. And this simple formula is the engine behind it all. The change it makes to each weight is just a product of three things: the learning rate, which is kind of like the size of the adjustment, the error, or how wrong it was, and the input itself. The key thing to see here is that the correction is bigger when the mistake was bigger, and when the input that caused it was stronger. It's incredibly intuitive. This table lays out the logic perfectly. Look, if the prediction is correct, the error is 0, so nothing happens. The machine says, hey, I got it right, no need to change. But the moment it's wrong, it nudges the weights in the right direction. It literally only learns when it messes up. Now, the perceptron was revolutionary, for sure, but its learning was a little, well, blunt. It knew if it was wrong, but it didn't really know how wrong it was. And this little distinction paved the way for a much more sophisticated way to learn. And that's where Adeline comes in, introduced in 1960 by Bernard Widrow and Ted Hoff. Adeline stands for Adaptive Linear Neuron, and its big innovation was nuance. Instead of just a binary right or wrong, Adeline could actually measure the size of its error. It knew if it was just a little bit off or way off. And how to do that? With a concept that is absolutely central to all of machine learning today, the cost function. You can think of a cost function as a single number that gives the model a grade on its overall performance. A high score means it's doing terribly, a low score means it's doing great. So the entire goal of learning suddenly becomes very simple. Do whatever it takes to make that cost score as low as you possibly can. So how do you find that lowest point? The process is called gradient descent, and the best way to picture it is like this. Imagine you're standing on a foggy hillside and you want to get to the very bottom of the valley. You can't see the whole thing, but you can feel which way is downhill right where you're standing. So what do? You take a step in the steepest downhill direction. Then you do it again and again. Eventually, step by step, you'll find the bottom. That is exactly what Adeline is doing with its map. But, of course, there's a catch. How big should those steps be? This is controlled by something called the learning rate, and it's a tricky balancing act. If your learning rate is too high, as you see on the left, you're taking these giant leaps, and you might just jump right over the bottom of the valley and end up higher on the other side. But if it's too low, like on the right, your steps are so tiny that it could take forever to get there. Finding that Goldilocks, just right step size is key. Okay, so this idea of walking down a cost hill is amazing. But what happens when that hill is shaped by, say, billions of data points? Figuring out the exact slope of that entire massive landscape before you take every single step, well, that would be incredibly slow. And this is where a really clever optimization comes in. The traditional method on the left is called batch gradient descent. It looks at the entire dataset to get a perfect picture of the hill and then takes one careful step. But the faster, more modern approach is on the right, stochastic gradient descent, or SGD. With SGD, you just grab one single example at random, estimate the slope based on that one piece of data, and take a step right away. Then you grab another one and repeat. So why would you take a rough, noisy guess instead of a perfect one? Well, the advantages are huge. For one, with massive data sets, it is so much faster. It also makes online learning possible, where a model can just keep learning as new data streams in. Sure, it might not find the absolute mathematically perfect bottom of the valley, but it gets incredibly close, and it gets there in a tiny fraction of the time. In the real world, that's often more than good enough. All right, let's tie all this together. It's time to connect these foundational ideas from the 50s and 60s to a super powerful algorithm that's being used all around you right now today. You see, those core principles we saw in Adeline, the idea of having a cost function and using gradient descent to find the lowest point, those are the exact same principles that power logistic regression, which is an absolute cornerstone of modern machine learning. So, what is logistic regression? It's a way to classify things, but it's way more sophisticated than a simple yes or no. It actually predicts the probability that something is a yes. So instead of just saying, it's going to rain, it can say, there's an 85% chance of rain. It pulls this off by using a special S-shaped function to squeeze its final answer into a neat little number between 0 and 1. And this kind of model is everywhere. It's used in medicine to predict the odds a patient has a certain disease based on their symptoms. It's what's behind the scenes in your weather app, forecasting that percent chance of rain. And it's used in finance to figure out the probability that a customer might default on a loan. Being able to calculate probability is just incredibly useful. Think about that for a second. This entire journey, which started with what was basically a simple on or off switch trying to mimic a brain cell, has evolved directly into these powerful algorithms that can calculate the subtle probabilities that really do shape so much of our modern world. But here's the thing. Everything we've talked about today was based on just one of these artificial neurons, which leaves us with a final massive question. These simple little decision makers were born in the 1950s. What happens when you stop using just one and you start connecting millions or even billions of them together?